Recording is about to start. I'm recording. That's good. So I think you see that. Yeah, everybody sees that it is recorded. And I share my screen. Let's see if that works. And screen sharing should be on. And I hope you can see my screen. Can you? Yep, excellent. And I have to say, somebody, I think it was Conrad, who said something in the chat just a few minutes ago, who made me think about a topic that I would like to discuss with you. Not today, but it fits really nicely. And I'm thinking about doing a session, perhaps tomorrow. Yeah, why not tomorrow? On Clown Watch. Let's do that. Let's do a session on Clown Watch and on data analysis. Because Conrad said something which I thought this is really interesting. I'll pick him up on that. So, blame Conrad for having an additional topic present. And thank you for the reminder regarding the attendance. Yes, please don't forget to register your attendance on Moodle. I mean, to be perfectly honest, if you forget the occasional attendance, am I too worried? Actually, probably not. But it is a criterion for people to see how engaged you are. To me, it is more important that you actually get the material, that you understand the topics. That's really the important thing, and that you can apply what you learn in these sessions. So that's really the important thing for me. I'm fully aware that I can talk to a room full of zombies who are there in person, but where the brain is switched off. Yeah, 300 only records audio. Is that right? That would be really strange. Yes, attendance was recorded in the labs. The demonstrators actually are walking around and note who is there and who is there on time. They do that pretty much straight away when the sessions start. So it says I was absent. Oh. Usually the attendance is, oh my God, do I have to sort out the attendance in labs? Oh no. I'll investigate, but don't stress too much. I mean, if your attendance goes below a certain threshold, then you have to have a meeting with your academic advisor and potentially with the senior tutor. But we are aware of the situation. So, look, guys, life is too short to stress too much about things. So don't get too hung up about things. And please mute your phones, not the phones, the mics. Otherwise, I know Bernardo is absolutely relentless with the clown watch list. Okay, I wonder who that is with the open mic. Aha. Theodore, please mute your phone, mute your mic. Does the Intro to Biochemistry module part cover week 3 as well? Not entirely sure if I understand the question. Are you talking about the multiple choice? Uh-huh. I think I've answered this question, but just for the benefit of the doubt, even without the material that we are going to do today and tomorrow, you should be absolutely fine to do the BI 300 multiple choice part. Okay, so let's get started because we've got a lot to do today, and I've got some stuff on my screen here that shouldn't be there. So first of all, a most wonderful good morning, everybody, and welcome to our BI 308 session. I want to shift a little bit gear because so far we have done molarities, making solutions, and also working with dilutions, as we did in the wash up to the practical yesterday. But I still want to stay with the practical because there is a lot that we still can learn from it. So yesterday and in the practical, you did the measurements, or you did one measurement at least, and you measured the absorbance. We also calculated the absorbance. Can somebody remind me, or somebody who has a very good memory, what the expected absorbance was that we calculated for what we measured in the practical? What was the absorbance? Yes, thank you. Absorbance, expected absorbance would be 0.22 or so. And I asked you how close you were. So, and Charlotte actually has put something really nice up because she has said that I gave you sort of an absorbance range, so from 0.2 to 0.25. And there is a whole sort of scientific field to making sense of these data. Morecambe says, I had 0.239, and he put a question mark behind it, right? And that gives me absolutely fantastic hook to what I'm going to discuss with you today. So 0.239 question mark. Is this a good result or not good result? What do you think? Is it good or not good? Good. Good, 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 good. Good result as it is in the range. It's fine. So what we are going to do today is we are going to talk a little bit about the concepts of accuracy and precision. And the best way to illustrate these concepts is with sort of a shooting target. So here I've got a target and I've got my bullseye. That's here, this 10 circle here. That's the target. And that is what I want to achieve. So in our case, this would be, for example, 0.22. But actually, Actually, 0.22, if we were absolutely sort of, what's the word here? Specific with our, with the way we phrase it, it would be just a single tiny little dot in here, right? And what I've just asked you is, how close is your measurement, or the 0.239, to our target? So what we do when we talk about accuracy, what we do when we talk about accuracy is we compare a measurement with a known target. And this known target can be through a calculation, or it could be a very well established target. This is the definition of accuracy. We compare a measurement with a known target. And that's really important. This is with the known target, if you like, is an external value. We compare our data with an externally derived target. So 0.239, we compared it with 0.22. And of course, depending on how big we make this bullseye here, we can say, yes, we are accurate, or no, we are not accurate. So I told you, let's make this target from 0.2 to 0.25, and then 0.239 would be pretty good in the middle. So we would have, let me just simply change the color. So we would have, for example, a hit here. Yeah, and this is within our target range. The size of this target that we have decided, that would be the limits, or that would be sort of a range in which we would say the measurement is accurate. Let's go for another one. Okay, is this one here, is the blue dot, is this accurate? Is the blue dot accurate? No. Okay. What about I make the target bigger? Now the target has this range. Is the blue dot accurate? Aha, now the blue dot is accurate because it is within the target range. Okay, let's do another one. Let's remove that. So we have our target range here. That is still our target range, right? Well, let's do another blue dot. Is this blue dot accurate? Aha, is not accurate. Now let's do a different dot. Is this light blue dot accurate? No. Semi. Oh, no, sorry. You can't be semi-accurate. It is a little bit like semi-pregnant. You can't be semi-pregnant. You are either pregnant or you're not. Is it accurate or not? Okay, what's your definition of being accurate? We haven't talked about precision, and precision here has nothing. We can't say anything about precision. Aha, it has to fall within the range. Absolutely right. Does it have to totally fall within the range? So actually, what we do is when we make this decision, is it accurate or not? We basically say we take the difference. So take the difference between measurement, our measurement, and the target. And if this difference is small, then we say our measurement is accurate. And of course, this difference very much depends on, if you like, the ranges that we identify. It depends on the size of the spots that we are looking at. So if the target is this size here, and our measurement is this one here, then we need to figure out, is there a difference? And depending on from where we measure, we can say, yeah, it's accurate. Here in this case, we have an overlap. So if we look at the difference between target in this area here, we would say, oh yeah, we are pretty accurate. So we need to be very careful when we define accuracy, because we need to be aware of the limits of our measurements. What is considered small? Alex, fantastic question. Emily, fantastic question. What is considered small? We need to figure out what actually is considered small. And we need to come up with an idea what we think is small. And we do that soon. Now let me go to a slightly different concept that people have mentioned. Under 5'6". Well, yes, that would be small. Or it would be large. I mean, if you are a tortoise, 5'6" tall would be, huge. So it really depends. Okay, let me remove that from my target here. Where's it gone? Okay, so we've removed that. Now, people mentioned the word precision before. We have now looked at accuracy, and we could measure accuracy actually just by a single measurement. We just shoot at the target and see how far away are we from our target. But people said yesterday they've repeated the experiment a few times. This is showing here. This is not a serious gun. People said yesterday, oh, I've repeated the experiment and I still didn't get the right result. This is where the term precision comes in. Precision means we carry out several shots or several measurements, and we don't rely just on a single one. We don't rely on a lucky punch, but we look at how close these measurements that we take, the individual measurements, how close are they actually together? So, for example, we might have a shot here. We might have a shot here. We might have a hit here. And now we need to make a decision. Are these three shots, are they close together or not? Yeah, they are. Well, it depends, doesn't it? They are certainly not terribly accurate because none of them hits the target. And they are pretty far away from each other. So when we said accuracy, compare a measurement with a known target, with an external target. For precision, we can say we compare measurements. We compare several measurements with each other. So that would be an internal comparison. An internal comparison. So if they cluster together, so for example, let me do that. If I, sorry, it's too many pens that I'm using here. If, for example, I had something like that, what do you think about that? The red dots, are they precise? They are precise. I compare them with each other. They are precise. Are they accurate? Precise, but not accurate. So how do we actually find out where our sort of boundaries are? We said, you know, what is small in terms of difference? What is precise? And obviously what we can do is we can do a little bit of, well, we can describe the data. We can describe this data set here, for example, and say, obviously we need to make a decision. Are they precise? Are they accurate? How far away are the data from each other when we talk about precision? So how far away from each other? Edith makes an excellent point here, because we can learn something. If the data are actually precise, it indicates that there's nothing wrong with the operator or the way they do something. There is a systematic error in it because the data are not accurate. It's a systematic error. And again, yes, there is an element which we will discuss in a different session of uncertainties in it. But I want to stick, for today at least, I want to stick with this: how far away from each other are the data? And it boils down again, how big is the difference? Now, of course, if we look at several data, we would easily run into a problem when we measure all the differences from each other. So therefore, the easiest way to deal with the concept of how far away from each other for several data is we just simply define one point as our reference point. And you all know how this is done. We can actually define the mean of our data. The mean of data. Yeah, and you know how this is done. I don't want to go to this 0.22 to the absorbance. I want to use a slightly different example to illustrate that, because the numbers are much easier. Let's say we measure the length of mice. We measure the length of mice. And let's say we have 3 mice. And we measure them from snout to tail. So we have centimeters. And let's say we have 3 mice, 14, 16, and 18 centimeters long. And what we can do is, which one do you think we should use of these data as our reference point? 16 cent. Why 16? Mm-hmm. It's interesting. There are people who deliver different explanations. It's halfway between the results. Aha, the closest to 14 and 18. So some people said we just simply use what is called the median. The median. The median is the value that is in the middle of a data set. So in this case, I've already ordered them nicely. And I just take the middle one. And the easiest way of dealing with the middle is I just simply cross out on both sides to get to the middle one. And that would be 16 in this case. Absolutely right. So that's the median. And the median very often is quite useful to work with. So that's a good way of dealing with it. But we can also define the mean, which is a different word for average. My maths teacher at school said I was average. I thought that was quite mean. How do we actually calculate the mean? And somebody has already said, what we do is we just simply add up all the values. I'm not entirely sure if that is politically correct. So we add up the values, 14 plus 16 plus 18, and we divide by the number of observations that we have. So in this case, it is 3. We have 14 plus 16 is 30. We've got 48 divided by 3, and that gives us 16. So that's the calculation of the mean. Or if we like, what we can also do, we can write this in a more general form. And the way we would write that is, and I give the explanation to that, we write this as this symbolized. What does that mean? N is the number of observations. So in this, observations. So in this case, it was 3. This here is an instruction. Take the sum. Take the sum. That's this Greek sigma, capital sigma, take the sum. And this x sub I means of all observations. Take the sum of all observation and then divide by n. That gives the mean. That is what this equation basically says. And we found, in this case, the mean is the same as the median that we observed earlier, that we discussed earlier. Now, what about how do the mean and the median actually differ from each other? Okay, how about we measure three little mice, 14, 16, and 70 centimeters, right? Obviously, what would be the median? Absolutely right. The median would be 16. What would be the mean? The mean would be 33.3 because I have to add them all together, which is 100 divided by 3. That gives me the mean. So what we see is that would you say that when we measure the mice, 14, 16, and 70, that everything looks right? Would you say that 14, 16, and 17, everything looks right? No, it doesn't, right? And somebody said, could you ignore it? Well, obviously what we would do is we would say, oh, wait a moment, that's 70 for a mouse. That doesn't seem right. But sometimes you just simply don't know. What if I had given you 23, for example, instead of 70? Would you have thought that 23 is a little bit odd? Yeah, this is difficult. So what we learn from that is that the median and the mean, the big difference between them is that the median is not terribly sensitive, not sensitive to extreme values. So let's call this 23, or let's do it again back to 70. 70 would be probably an extreme value, but the mean is not sensitive to it, whereas the median is not sensitive to it, but the mean is sensitive to extreme values. And what we also see is that the mean and the median don't have to be the same thing. We can do them both totally independent and get two different data. If we do that, we probably need to ask ourselves what the heck is going on. Which one should we actually eliminate? Some people suggest 14 has been voted out, 70 should be voted out. Which one should we ignore? 70. I like your way of thinking. We come to, I will discuss that, Ella, in a minute. I like your way of thinking. You say you want to vote one out, right? You want to vote one out, but why? If we measure what we measure, then this is what we get. It's not an imposter, it's what we measure. So instead of voting one out or calling one imposter, what we need to do is we need to say, wait, this does not look, this is not exactly what we expected. So what we really need to do is we need to go back and say, where did we go wrong? Mute, please. Oh, I saw mute. Aha. Get more results? Yes, we could do that. Absolutely right. Now let's go back quickly to the median. So we have 14, and it would be really great if themselves. It obviously shows me that they're not listening, but that's so we have 14, 18, 23, 12, and 15. So in order to find the median, what we need to do is we need to sort the data from smallest to largest. So let's say that is 12, 14, 15, 12, 14, 15, 18, and 23. And then we just simply find the middle one. And the middle one is, what we can do is we can just simply strike off from either end like that, and I find the median is 15 in this case. Okay? Now here's a question for you. 14, 18, 23, 16, 18, 12. Where is the median? Because now we have a little bit of a problem, don't we? Let's do it. Let's sort it. So the smallest one is 12, 14. We have 16. We have 18 and 18 again. That's this one, and 23. So let's go and strike them off. 12, 23, 14, 18. Now we have a problem. We don't have anything in the middle, do we? So how are we going to deal with that? Well, we just simply say we take the average of these two. The average is the number exactly in between. So we take 16 plus 18 divided by 2, which is 17. So the median for that would be 17, although we don't have this number present. So if we have an odd number of data, it's very easy because we just simply, like we had here, the odd number. If we have an even number, we need to find the number in between the two numbers that are around the middle. Does that make sense? So mean and median. Good. Let's come back to our problem with the target practice. And we said we have these numbers, or no, let's go back to 14, 16, and 18, our mice in centimeter. And we've established we can use the mean in this case, which is 16, and use that as our reference point. That's the reference point. Okay, and now we can actually determine how far away is every other measurement from this reference point. How far away is a single measurement from reference? And the reference point, that was the one that we have chosen to be sort of representative of what we have measured. The reference point is 16. And this is for precision, absolutely right. So what we can do is we can say, right, what we just simply do is for the first point, our first measurement, x1, that was 14. 14 minus 16, we just simply take the difference. Very good question. Is the mean always the reference point? We usually tend to do that. Yes. And I also have to say, what I showed you here, this equation here, this is actually what is called the arithmetic mean. There are other means, but they're usually not considered of that much importance for what we are doing. And the mean is usually considered as the reference point when we look at data. So we can say, right, the first measurement is 14 minus 16, so that's -2 away. That's the first point from the reference, or the first distance from the reference. The second, how far is the second point away from the reference point? Don't forget we have 3 data. How far is the second point away? +2, 2, 2. Ah, somebody says 0. Actually, this is the second point here. This would be 16 minus 16. So the second point is away 0. And the third point would be away. How far is the third point away? +2. So because it is 18 minus the reference point, and that is always the reference point. Yeah, this is our measurement, and I indicate that by xi. And this I just simply stands for the number of the measurement. So xi, x1, 14 minus 16 equals -2. x2, where I is 2, 16 minus 16 is 0. And xi, where I is 3, that's the third point, 18 minus 16 is +2. And what I can do is now I can say, right, on average, how far on average are the data point away from the reference point? How far are the data away from reference point? So what we need to do is we just calculate the mean of these data here. So we calculate the mean of -2, 0, and +2. And what we get is Abdul Rashid got it right. So we have -2 plus 0 plus 2 divided by 3, and that gives us 0 divided by 3 equals 0. Hey, wait a moment. We have a problem here. There must be an error because we've just calculated how far on average every point of the measurement is away from our reference, and we found that it's 0. That means our points are identical to the reference point. The distance between, on average, the distance between our measurements, you can divide a number, you can divide 0 by a number, but you can't divide a number by 0. But this is perfectly valid. So there is something weird going on. Actually, it turns out that we can't do it like that. What we actually want to do is, instead of taking the sign count, we have -2 and +2, we need to get rid of the signs. And what is the best way of getting rid of a sign in front of a number? Multiply by -1. That's interesting. That probably causes another problem, because if you've got a positive number times -1, that gives you a negative number. If you've got a negative number -1, that gives you a positive, so you don't get rid of it. But people say we can square it. So instead of calculating the mean, what we can do is we can calculate xi minus the mean, and we square that. So we do that for the first number, and then we do the same thing, x2 minus the mean, we square that, plus x3 minus the mean, and we square that. And then we divide this by 3. Does that make sense? If we just do it without squaring, we get 0. That's actually sort of the underlying principle of the arithmetic mean. But if we square it, then we can say basically what is the true difference, but it is the square, but we can add them up. Do we get 0 when we do that? Let's have a look. So we had 14 minus 16 squared plus 16 minus 16 squared plus 18 minus 16 squared divided by 3. So what does that give us? 14 minus 16, that's negative 2 squared plus 16 minus 16 gives us 0 squared plus 18 minus 16, that gives us positive 2 squared divided by 3. Negative 2 squared gives us 4 plus 0 plus positive 2 squared also gives us 4 divided by 3. And we put that together. That gives us 8 over 3 or 2.67. So this means we have the average square. That's the important bit. The average square of the difference between the data points, let's call it data points, and reference point is 2.67. So this is the average square. And because everything has to have a name, this is also called the variance. The variance is the average square of the difference. I can write this actually. The variance is given. What have we done? We've taken the sums xi minus the mean. We've squared that and we divided it by the number of our observations, n. And I will discuss with you when we use the variance. There is another thing. When do we use the variance? That's an excellent question. And I will show you how we apply variance for our precision in the session tomorrow. Thank you very much for watching. Watch that space. This is going to get very interesting because we will do some fancy stuff with that. So, see you tomorrow. Please, if you've got any problems with watching the videos on Moodle, my colleague, Dr. Mark Was, has sent out an email, and I think I put that on group chat and other places. There is a workaround. So if you run into problems, please have a look at that video. And then I see most of you probably this afternoon in BI 300. And as you have seen, I made a big boo-boo. The session this afternoon is from 3 to 5, where we will go through the kiwi fruit extraction practical, and we will mess around a little bit more with nucleic acids. See you this afternoon. Take care. Bye-bye.